All right. So we were taking a look kind of throughout all of Unit 9. Last time was a little bit of application with this idea, but I have been looking at systems of equations. What we're going to look at today is very much related to systems of equations. We are not going to get too deep into the weeds here. If you would like to get too deep into the weeds, take a linear algebra class in college. And if you want to get deeper into the weeds, take a vector spaces class in college. And then you can deal with matrices where you don't have numbers, but where each thing is a separate function. And you can do cool things like rotational matrices and all this fun stuff. It's really, really deep. Like, it's its own branch of incredibly useful, incredibly powerful mathematics. We are going to very much be scratching the surface here. And what we're going to mostly be focusing on is kind of a basic set of operational skills with these, rather than, again, going for a lot of that, like, really, really refined depth that we can get to. So this is very much me holding myself back from spieling ad nauseum about matrices. We're going to not do that. Okay. For our purposes, and again, there are different ways to think about this, which give you different things, and they're all really, really cool, and we're not going to worry about it too much. But for our purposes, matrices are ways to represent essentially kind of like a simplified version of a system of equations. So for instance, if we had the system of equations, we'll say 3x minus 2y, and then 4x plus 7y, and then negative x plus y. We could write this as a matrix using just the coefficients for x and y. So this as a matrix would be 3 and then negative 2. It would be 4 and then 7, negative 1, and then 1. Again, there's a lot more to say here about like vectors and blah, 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 blah. Not going to get into it. Not too much. Today we're going to focus on primarily terminology. When we are talking about matrices, one thing that is often going to accompany a matrix, because we have a lot of flexibility for things like number of variables that we are using in our system, number of different equations that we have for that particular system, the size of the matrix can vary a lot. And this goes beyond just like our vector dimension, which we saw a little bit before, because we have both columns and rows to consider, which we didn't before with our vectors. So in this case, we would describe this as, you'll see this as an M by N matrix, where M represents the number of rows and N represents the number of columns. So for instance, what kind of matrix would this example be? Yeah, this is a 3 by 2 matrix. Okay. To make things a little more complicated, but also there is some. Another way to think about the number of rows, this is also describing the size of each column. Right, my column is going to be as big as I have rows. If I have 5 rows, each column will have 5 entries. And so the number of rows we can think of as the like column dimension, which is just the size of the column, and the number of columns we can think of as the row dimension, or the size of the rows. It makes it confusing. The number of columns is how big each row will be. The number of rows is how big each column will be. And I'm making this distinction for a later operation that we will see, where what we want to say is that the size of rows must match the size of columns. And what that means is that the number of columns must match the number of rows, things like that. Let's go ahead and call this vector, not vector. Let's call this matrix A. If I want to refer to a generic entry within a particular matrix, the way we do so is of the form A sub ij, where I tells you the row number and j tells you the column number. So for instance, for this particular matrix, what would A sub 1, 2 be equal to? What does the 1 represent? Row 1. What does the 2 represent? Column 2. What is the entry that is in row 1, column 2? Negative 2. Versus A sub 2, 1 would be 4. Second row, first column would be. So I is your row number, J your column. Yeah, so if we go 1, first row, second column, that takes us to that. Second row, first column. Okay. The first two operations that we're going to look at are actually ones that we're just not going to spend time on at all, because they are very intuitive. What I'm going to say, try the matrix addition and try the scalar multiplication, doing it how you would expect it to be done. So try the first two examples. I'm not going to tell you how they work. I'm just going to say, try it, see what you get. Yep, don't overthink it. So this is.
Well, that's crazy.
It's Tuesday.
I got 8 bucks. Find 8 months. Oh, my leg hurts. I'm not. Downstairs, put clubs on this. And yet you're the one still laughing. Not for clubs.
And then do the, which again, exactly what you expect. Yeah, just the. We'll do this specific. Now when I. So drive. Well, what did you do?
How about just? No,
Nice. You do the subtraction and the scalar. Yep, those are good.
Oh, we're doing the scalar one?
Those are good. Yeah, try the scalar ones. Again, exactly what you expect.
Oh. Wait, oh. That's really showed you.
Well, so much.
No, but see, they just.
These are good. Okay. What did you guys do for our matrix addition? What'd you end up getting? So 5, whoa, 5, 2, -3, and then 4, 5, 0. What'd you do for this? You just add the components that line up? If we are accomplishing our matrix addition and matrix subtraction, same thing, but you subtract. If we are doing this by adding the components as they line up, what must be true about both of the matrices with which we are working here? They have to be the exact same size in order for us to do it, right? If we had a 3x2 and a 3x3, they're not going to line up, right? There's going to be an extra column missing, and we're not going to be able to do it. So in order for us to be able to do our addition and subtraction operation, the size of the matrices must match exactly. And then scalar multiplication, you just like multiply everything by that particular scalar, right? So taking, like, for instance, if I did 2 times a, I would get 4, 2, and 2, and then 12, 0, negative 6, right? You just multiply every single component by whatever that scalar is. So those ones are the kind of intuitive ones. They work exactly how you would expect them to work. Never mind. The new operation, as it comes with matrices. And again, we're not getting into the weeds about like what these operations are trying to do. We're just going to, again, go through this very mechanically. Is matrix multiplication. So let's say we have the matrices. We'll do 1, 3, -2, and 4. And I'm multiplying this by the matrix 5, -7, 2, and 1.
Is this on here? Did you just make?
No, I'm just making this up as like an example. You guys have a very detailed list on your notes of how to do this. I'm going to try and not do that because I think when you try and describe it like that, it becomes way more confusing than is necessary. I'm just going to showcase what this is going to do. What's a little bit weird about matrix multiplication, you can imagine a world where, oh, we just do 1 times 5 and 3 times -7. Does not work. The way that we define matrix multiplication is as follows. We take the rows of the first matrix and multiply them by the columns of the second matrix. So we're going to consider the rows, in this case 1, -3, and 5, 2, -1, taking these rows, these columns, and we're going to multiply them together. But what multiplication here looks a little bit different. We are going to be taking the first component of each and multiplying them. We're going to take the second component of each, multiplying them, and then we're going to take the sum for each piece. And what that will give us is the coordinate for a particular location in our matrix, determined by which row is being multiplied by which column. Which sounds like a lot. Again, let me showcase. So for instance, looking at this particular problem, I'm going to take my first row and I'm going to multiply it by my first column, and that is going to give me my 1, 1 entry. That will give me my first row, first column entry. In this case, first row times first column is 1 times 5 plus 3 times 2. So first multiplied together plus second multiplied together. And that's my entry for 1, 1. If I want to know my entry for first row, second column, I'm going to take, again, the first row and multiply it now by the second column. What is that going to look like here? 1 times -7 plus 3 times 1. That is my first row, second column entry. Let's do my second row first column entry. What is that going to look like? Perfect. Plus 4 times 2. Very nice. And then my second row, second column. Yep. Very nice. Perfect. And that gives us a new matrix. In this case, we would get, I'll go ahead and say what this is. This would be 11, -4, -2, and 18. (14 plus 4). Now, in order for us to be able to do this, what had to line up here? The dimensions of which had to match. So the dimensions of my rows from my first matrix had to match the dimensions of my columns. In other words, dimensions of my rows is the number of columns. My column number had to be the same as my row number for matrix A versus matrix B. So this is, again, why thinking about, I think the size of the row as that like second entry and the size of the column as that first entry is helpful in this context for our matrix multiplication. Questions here about our process? How's this feel? Done this before. I struggle to remember which one's rows, which one is columns. This is not even just for you guys. I do this on my paper every single time I do a matrix multiplication problem. I circle the rows that I'm going to use, and I circle the columns that I'm going to use. It just kind of helps me keep track of my mind. Probably in algebra 2. Yeah. Okay, let's take a look at an example here. That's why we're going through this faster than we normally would, is because it's a fair bit of this in algebra 2. We'll get to some stuff that we haven't seen though.
Is this how you multiply like all of them?
Yeah, this is how we would do all of the matrix multiplication. But again, the size matters here. So some are invalid, some we're not going to be able to multiply. We'll see an example here in just a second. So looking at our first example here, we are trying to find both A times B and B times A. Now, something that we kind of take for granted with a lot of our operations is the property of commutative. What does it mean for an operation to be commutative?
Around the numbers and having that more.
Yeah, we can mess around with the order in which we are doing the operations, right? So 2 plus 5 is the same as 5 plus 2. 7 times 4 is the same as 4 times 7. Those are because those operations are commutative. With matrix multiplication, order is really important. What does order determine when we are doing our matrix multiplication?
What
Yeah, it determines which one is rows, which one is columns. So for instance, if I were to reverse these two matrices, I now actually no longer care about the columns of this matrix. I now care about its rows. And I no longer care about the rows of this matrix. I would then care about its columns, and you would get a completely different product. Okay. So in this case, order is really, really important. We take it for granted, but know that A times B and B times A aren't necessarily the same thing. And as we're about to see, one of them can be a valid product and the other one might not be. Okay, so let's take a look at this setup here. We are trying to find both of these products if possible, although what I want to determine is which one will be possible and which one will not. A, B, which in this case, -1, 5, B, 2, times 3, 6, 4, -8, 0, 12, And so this is AB, BA, which is same thing but reversed. So 3, 6, 4, 8, 0, 12 times -1, 5, B, 2. Of these two, which one will yield a product? So what do we care about from our first matrix, and what does that have to line up with in our second matrix? So the size of the rows of the first matrix have to match the size of the columns in the second matrix. Which one has that as the case? I think AB has that as the case, right? Because these are a size of 3, which is too big for these, right? Versus these are a size of 2, and these, oh, messed that up. These are a size of 2, and these are a size of 2. Okay, so BA is impossible. Can't do that one. Work with your group. Take AB.
Do those. This is first. Try and do 3 to 6 of the. Times -1 seconds. You can do 3 times -1. Make your 6 times 3, but then and so we would be. So it's just that it's actually like they don't match. So does that get it's land? That's a long problem. Yeah, go on. Grab the basket. Yeah. Doing that multiple.
In life, you don't always have calculators.
Yeah, how often have we had tasks?
Oh.
Yeah.
You knew.
We're doing A times B.
Yeah, because we can't do view.
Yeah, facts.
It's like
Well, you're doing, so your first row, first column would be the -1, 5, and the 3, -8. So you do -1 times 3 plus 5 times -8 will give you your upper left corner. So first row, right? First row has to be column. -3 plus.
6.
Can you?
I'm saying.
So this times this. Minus.
Say it. So are we gonna end up with one like this?
Yeah, what about that?
Or it's?
Yeah.
My favorite. Yeah.
Right. Oh, I can see. Yep. Exactly. Yep.
So. What do you do?
I need to get break.
What do you?
It's okay. You get 4 hours to be right here. No, I'm gonna send you to. You can. Literally 3 cabins. We did it by chicken. And our times are called. It went pretty well. I was like, everybody next.
For real?
Very nice. Very nice.
Go fast. Thank you. It's something like a 6 week.
Oh, that's.
Right? Like it's like important.
I don't know. Beautiful.
You're saying. Yeah, otherwise it's.
Wake up. The first of the month.
My phone is not internet.
First. Wake up.
So first row, first column is first row times first column. Second row, first column, second row times first column. And then first row, second column.
No, that's even.
First row, third column.
This one just following this guy.
Wait, think what? No, 1 second. Wait, she can. Someone
Sure.
has to arms.
Stella, how'd you compute the first row here?
Negative.
Oh,
I never have it written down. Do you want it like the answer I got or like?
well, how'd you compute it? Yeah, tell me your process.
-1
Yep,
+5 plus -8.
perfect. So that gave us negative 43.
Yep.
Yep. Yep. Very nice. Yep.
5,
Yep. 56.
6.
Very nice. And then exact same thing for our second row, but instead of using the -1, 5, we use the 3, 2. So 3 times 3 is 9, plus 2 times -8, -16 gives me -7. 3 times 6 plus 2 times 0 is 18. And then 3 times 4 plus 2 times 12, I get 36. Questions about matrix multiplication? Someone in first period asked me a question that I really liked. That I really liked a lot, actually. Which was, well, if we have matrix multiplication, well, it's a very natural extension of what we would expect to find. Matrix division. How would we do matrix division? And the short answer is that division as an operator doesn't exist. And subtraction as an operator doesn't exist. What is division really? Multiplication of the inverse, specifically the multiplicative inverse, which we call the reciprocal. Okay. What is always going to be true about the product between a number and its multiplicative inverse? It's always equal to 1, right? 5 times 1/5 is the same as 57 times 1/57 is the same as 2/3 times 3/2. Always that product is going to be equal to 1. In the same way, we found additive inverses. What is always true about the sum of additive inverses? It's always equal to 0. 7 and -7. 2/3 and -2/3. Always adding to 0. Where 1 and 0 are the do-nothing elements for those particular operations. Right? If I try adding 0, or if I try multiplying by 1, I'm not going to see anything. And so we don't have matrix division, but what we do have are inverse elements for matrices under the operation of matrix multiplication. And what's always going to be true about the product of two matrices that are inverses is they are always going to reduce down to what we call the identity under matrix multiplication. And the identity for matrix multiplication is actually fairly simple. It's going to vary in size because matrices vary in size. But if I have what we call I sub 2, which would be the 2 by 2 identity matrix, this is going to be a matrix with ones on the central diagonal and zeros everywhere else. Similarly, my 3 by 3 identity matrix, ones on the central diagonal, zeros everywhere else. And we could even have I sub n, which would be again 1 on the central diagonal and zeros everywhere else. So our identity matrix, always of this form. We have ones all the way across, nothing anywhere else. And inverse matrices are ones where A times its inverse is the same as its inverse times A is the same as some identity matrix, whatever the appropriate size of identity matrix would be. This gives us a fairly simple way to check if two matrices are inverses of one another. The easiest would just be to multiply them together and see if you get the identity matrix. If yes, then you're done. What's more interesting to me is finding the inverse of a particular matrix using this definition, using this setup. So I want to take a look at this example. We are given that matrix A is equal to, actually, I'm not going to do this. We're given the matrix -1, 5, 3, and 2, and we are trying to find its inverse. Okay. What must be true about this matrix and its inverse? What is the one fact about inverses that we know? How did we just define the inverse matrix? I'm looking at the second page. It's the one straight below.
Oh, it's the one.
Yeah. Look. Yeah, it's the same numbers. It's just like the 1 and the -1 and the 3 are swapped. What was our definition for an inverse matrix? Yep. Equals the identity, which is just, again, the matrix with all ones along the diagonal. And so if I take this matrix and multiply it by its inverse, we'll use a generic matrix. We'll call this A, B, C, and D. What should this be equal to if in fact they are inverses? 1, 0, 0, 1. All right, and now all we have to do is solve for A, B, C, and D. Let's try this out. How would you guys go about approaching this problem? What would you do? That's probably not going to be very successful. What would you do here? Yeah. So how do we do the matrix multiplication? What do we have to remember? Rows times columns. So what is this product going to look like? You have B and C swap, but it doesn't matter. For me, it's B, but that's fine. Yep. And it's going to equal, yeah, that'll be the system that we generate. I'm going to do the matrix first, and then we'll turn it into the system that you're generating. So our first upper left entry, -1 plus 5b. What would our row 2, column 1 entry look like? That would be row 1, column 2, but we can do that. -c plus 5d. Yep. What would row 2, column 1 be? Yep. Very nice. And then row 2, column 2. Plus 2d. Very nice. And what should this be equal to? 1, 0, 0, 1. Which will give us exactly what Addy was pushing for here, which is a system of equations. We'll essentially get two 2x2 systems of equations here, where we can solve one for A and B, or A and C, whichever arrangement you had, and the other for the other two. So what is my A and B system of equations here? What should my first entry be equal to? Very nice. And what should my row 2, column 1 be equal to? Very nice. And for my second system, what should my upper right be equal to? Very nice. And my final? Very nice. And from here, we're just doing a 2x2. Let's go through that really quickly. How would you guys find A and B? What's like probably the easiest way to do this? We could do elimination. You can multiply the top row by 3 and then add them together. I like that. I get that 17b is equal to 3, which gives me that b is equal to 3 over 17. He suggested elimination here, so multiplied this row by 3 and then added the two together. Yeah. So 17b equals 3, b equals 3 over 17. Plugging it back into my original, I get that a should be equal to -2 over 17. Get negative a is equal to 1 minus 5b, 1 minus 15 over 17 is 2 over 17, make it negative. And then over here, again, we could do an elimination setup, maybe multiply by 3 and then add. I get that d should be equal to 1 over 17. And if that is the case, c should be equal to 5 over 17. Here, if the elimination is being a little bit weird, solve this for A. A is equal to 5b minus 1, and then just replace this for this and solve for B. Yeah. Likewise, we could get that, this is what my other period did, that C is equal to 5d, and then you could take this and plug it in here. Either way is fine. And so our inverse matrix here, we said A, then B, C, then D. This is -2 over 17, 3 over 17, 5 over 17, and 1 over 17. Questions? Finding matrix inverses. How's this feel? Terrible? Mostly just a lot of steps, I find. None of the steps individually are all that crazy. It's just a lot. We'll see that as especially true tomorrow. Okay, one final thing that we are going to look at, and that is the determinant of a matrix. There are essentially two different ways to calculate this. This is something that only applies to square matrices, I'm fairly certain. Don't fact check me on that. Take everything that I say generally like that with a grain of salt. But I think that's the case. The easiest case by far, and probably the one that you have seen if you have done work with matrices, is the 2x2 determinant. So for instance, if we're considering our matrix A from before, which was -1, 3, 5, and 2, and I want to know the determinant of A, the way we do so is fairly simple. We do A times B minus B times C. In this case, this would be -1 times 2 minus 3 times 5, which is equal to -17. There's more that could be said about the relationship between the determinant and the matrix inverse. But I'll leave you to play around with that. Determinants and their relationship with inverses. So again, determinant generically of A, B, C, D, AD minus BC. That's the easy one. The hard one are the big ones. A 3x3 or a 4x4 or a heaven forbid a 5x5. Right? They scale in difficulty probably like exponential. Difficulty, not necessarily difficulty, but like the number of steps you have to do increases significantly with each size step up. You guys have like this whole list of instructions on the back of your notes for how to do a 3x3. I don't do my 3x3. I don't find that to be intuitive. I'm going to show you a completely different method, which I like a lot more and which I think extrapolates upward a little bit better. Which is just to say, what we do here for 3x3s, you would do the same thing for 4x4s. You would do the same thing for 5x5s. You're going to get the same result. Okay. So let's say we have a 3x3 matrix. I want to know the determinant of, we'll do A, B, C, D, E, F, G, H, I. What we are going to do is we are going to start by picking a row. It doesn't matter which row, actually. As long as you are staying consistent and you're staying within one of these rows, you can pick any row you want. But maybe pick one that's going to be easy. Generally, I find people pick like the first row or the last row. If you wanted to, though, you could pick the middle row, and that's fine. So pick a row. Pick a row. Do you guys have a preference for how you would like to do that? First row. Sure, fine. Let's pick the first row. We are going to look at the first column entry in the first row, which in this case is A. And we are going to take A and we are going to multiply it by the determinant that we construct using the other entries that are not in its row and not in its column. In this case, what would the 2 by 2 matrix look like that doesn't share a column or row with A? E, F, and HI. Our first piece of this determinant is A times the determinant of E, F, HI. We slide over. When we slide over, we're going to alternate here between plus or minus. So positive, negative, positive, negative, positive, negative as we go. So next entry is going to be a minus. I am now looking at D, which I will call.
If you were to do that, would
Yep.
it be E times?
Exactly. And then distribute the A through it. Yeah. Yeah. Important to note here, we are taking determinants, right? This is the determinant of that 2 by 2. Good question. So I slide over to D and I do the same thing, except now because it's my second entry, we're going to do subtraction and stuff. What would the 2 by 2 matrix look like that doesn't share a row with D and also doesn't share any columns with D? That would be B, C, and HI. So that would be these and these. We move over again. Now we are back to plus. Now we are looking at G. What is the 2 by 2 that doesn't share any rows or columns with G? B, C, E, F. So this is G times the determinant, B, C, E, F. And you would just run that to get the determinant of the 3 by 3. A 4 by 4 would be the exact same process. You pick a row, you work your way through the columns, you alternate plus minus as you go, and you would get 4 3 by 3s, each of which you would then need to reduce down to 3 2 by 2s, which you could then evaluate. A 5 by 5 would give you 5 4 by 4s, which each of which would then give you 4 3 by 3s. Each of them would then give you 3 2 by 2s, which you could then. You'll notice here what this would be like a factorial scaling in terms of like the number of operations that we have going on here. It gets obnoxious fast. We probably won't do anything. I might make you do like the setup for a 4 by 4. I probably wouldn't. Try the final example here. So find the determinant for 1 1 1, negative 3 1, negative 2, 7 1. Yep.
Here, and you do this, what do you do with the one outside?
You-
multiply it, it'd be one outside.
Exactly.
It'd be a negative.
So you're distributing.
And are we putting this into a two matrix stuff? So we get.
No, you should get a value.
No, it's a value.
Yeah, you'll just get a value. Yeah.
No, we do.
It's the answer.
Multiply this by negative seven, or by this, yeah, you just forgot this. This should be, if you alternate, so you do plus minus plus, pull it out. Yes.
At least there's only 18 of them.
I don't know what's that.
It's up there one.
Sure, yeah.
That one, you
Yeah.
Yeah,
I see, that's the thing, it's like I can somewhat, but I don't know, I just showed them. You were. Seven looks really good.
Was this here? What was your? What was your?
I think other than.
I'm sorry. Get my water. Get my water.
You don't care to change that? You're not gonna get scammed.
Get my water.
So, yes, but that'll be me. One times negative 10 minus 100. All right, how about this as my setup? Again, this isn't the only way to do it. Not the only way to do it. I could have picked a different row and you would get the exact same thing. That's totally fine. But I got negative 10 as my determinant at the end. All right. Questions with our matrix operations? All right, what is due tonight? WebAssign, what do we have tomorrow? Quiz over 9294. Yesterday and Friday.